Welcome back. Today we're going to start chapter 10, Parametric Equations. The idea for this chapter is basically not always you have equations of functions in terms of, let's say, y equal to f of x. Not always this is possible, but sometimes you have curves that you can rewrite in terms of an extra variable. And how we can do that is we introduce a new variable, let's say t or theta, depending on sometimes theta using for angles, or even t would be able to be used for angles as well. So t is a variable, and you want to represent x and y in terms of variable t. So basically x is depending on t, as well as y is depending on t. So if you're looking for a point, x and y, you just need to pick one value of t, replace in both, that gives you a coordinate of x and y. So x and y coordinate basically would be depending on the t value. It gives you a value for x, f of t, and g of t will give you a value for y coordinate. So to make it more clear, let's look at the next example. Let's say they've asked you to sketch this curve. We don't really know how the curve looks like at the moment. X has been represented by a variable t, and on the other side y has been represented by the same variable t. So x and y are related to each other by the same variable. If this was in terms of, let's say, instead of t, if it was z, then you cannot relate x and y. So here we have t plus 1. Let me go back into color. Okay, and we're trying to sketch this. So how do you do it is normally the same idea that we had for x and y. So we draw a table for x and y, but now x is already depending on t, so I'm going to add an extra column for t. And let's say we pick t to be -2, -1, 0, 1, and 2. Figure out the corresponding x value and y value. So if I pick t to be -2, replace -2 into the equation for x. So I'm replacing -2 here for t. What do you get is -2 squared is 4, minus 2 times -2 would be 4, so you would get 8. As we get x to be 8, what do we get for y value? If I replace -2 for y, what do we get is -2 plus 1, which is simply -1. So now I have a point, the x and y coordinate of that point is basically 8 and -1. Similarly, if you replace -1 for t, what would you get is 3. And if you replace into equation for y, we get 0. So we have 3 and 0. What if we replace 0? We get x to be 0, t turns out to be 1. So you get 0 and 1. And you can continue, pick more points. Let's try 1. 1 gives us -1 for x, and what do we get for t? It would be 2. So we have -1 and 2. And if we pick if we pick t to be 2, then we have 0, and y value would be 3. So here is one thing that you should notice right away. This curve is not going to be represented by a function, because now you have the same x value, but different y values. That means you cannot write y in terms of a function of x. This is not a function. This is just a curve that has been represented by another variable t. So let's draw these points. Okay, here we go, x and y axis. Let's find these points, 8 and -1. Here's 8, here -1. So here 8 and -1. And 3 and 0. Let's say 3 is here. It's 3 and 0. Then we have 0 and 1. 0 and 1. We have -1 and 2. Here's -1. Y value of 2. And we have 0 and 3. 0 and 3. So the curve that we have, we're going to go through all these points. And you kind of can pick more points, and you will notice that this curve would look like something like this. And definitely it's not a function. It's a parabola sideways, but if you draw a vertical line and crosses multiple points, so it's not a function in terms of y cannot be written in terms of x. But you can relate x and y. You can get rid of the variable t if you want and write it. So this is the sketch of the curve, but you can relate x and y. How do you do that is in one of the variables, for one of the variables you get rid of t. You solve for t. So here the easiest one would be we have y equals t plus 1. So what is t? T equals y minus 1. So now I can replace x is t squared minus 2t. Instead of t, I can replace y minus 1. So I can say x is y minus 1 squared minus 2 times y minus 1. And what do I have is a relation between x and y without the variable t. So this is another way to look at the equation. Basically, what you're doing is you're writing x as a function of y in this case. Let me not use, actually I can do that. Okay, again, not always possible to be that neat and clean, but the idea is always the same. You can draw this table, create a couple of points, and sketch the curve. The more points you pick, the more accurate the curve becomes. Okay, here's another example. What kind of curve has been represented by the parametric equation x equal cosine t and y equal to sine t, assuming t is between 0 and 2 pi. So these angles are always in radian, because we're assuming t is a variable and there is no circle to say t is the angle in degree. So make sure that you're using radian. So again, you can always draw a sketch of the curve, then try to see if you can find the relation between x and y. Here I'm going to pick t, x, and y. I'm going to pick t to be some angles in radian. 0, pi half, maybe pi fourth, pi half, pi, and finally 2 pi. You can pick more points. You can pick 3 pi half if you want, and then 2 pi. What is the corresponding x value? X value is cosine. What is cosine of 0? It is 1 cosine of pi over 4, root 2 over 2. Cosine of pi half, that is 0. Cosine of pi again 1. 3 pi half would be 0. Here is negative 1, sorry. And 2 pi would be 1. Corresponding y value, if you replace t with 0, sine of 0 is 0. Sine of pi over 4 would be root 2 over 2. Sine of pi half would be 1. And here we get 0. We get negative 1 and 0 again. So now I kind of have a couple of points if I want to draw. I can draw them. I'm looking at these two columns now, x and y coordinates. So I have the point 1 and 0. 1 and 0. This is 1 and 0. I have root 2 over 2 and root 2 over 2, so somewhere here. Root 2 over 2 is like 0.7, so this is 0.7 and 0.7. And then I have 0 and 1. Next we have negative 1 and 0. Then we have 0 and negative 1. And we go back to 1, 0. And you kind of can expect the curve to look like this. And what you notice is basically you will get a circle. You cannot guess that it's a circle. You have to pick more points just to see if it's exactly a circle or not. Maybe this is not going to be a circle, but in this case, it kind of tells you that the x-coordinate is corresponding cosine, y-coordinate is sine. If you remember, if you pick any point on a unit circle, the coordinates are cosine, theta, and sine theta, given the angle theta. and which is exactly the same as what you have here, cosine theta and sine theta for x and y coordinate. But if we didn't know that, how would we represent this curve? You can always try to get rid of the variable t. In this case, the technique is to kind of find the relation between cosine and sine. The easy way would be x is given sine t, y is given cosine t. So now, what would be x squared? This is sine squared of t. What would be y squared? It would be cosine squared of t. Why did I square it? Just because I know sine squared plus cosine squared equals 1. So now if I add both sides of the equation, on the left side you get x squared plus y squared. On the right side you get sine squared plus cosine squared. Sine squared plus sine squared t plus cosine squared t. This is 1. Most of the time the technique to get rid of sine and cosine is by doing that. Square both sides and add them together because they simply turn out to be 1. And what we have as an equation is x squared plus y squared equal 1. And this is equation of a circle with center 0, 0 and radius 1. So here is the radius of the circle, just simply 1. Okay, so this curve actually represents the unit circle. Okay. Another example, find a parametric equation that represents a circle with the center h, k, and radius r. So now this is a more general one. We talked about the unit circle. So let's say we have a point hk somewhere here, h for x, k for y. And you have a circle of radius r. So this length is r. Okay, then the question is, what is the parametric equation that represents the circle? Always the easy way is ignore the center. Assume the center was 0, 0. What would you do for the parametric representation? So let's say you have a circle with the center of 0, 0 and radius r. As we did in the last example, for the unit circle, we had x equal cosine t, and for the y coordinate we had sine t. This was if we have a unit circle, which means radius 1. But if you want the radius to be r, you just need to rescale it. R times this, r times that. That is a circle with the center 0, 0 and radius r. This is a parametric equation for that. But what if the center was not 0, 0? What if it was at h and k? H is the corresponding x coordinate, k is the corresponding y coordinate. So what I'm going to do is I'm going to shift the circle. I'm going to shift this unit, circle with the center 0, 0, up k unit and right h unit. So here, what would be the representation? It would be h plus r cosine t, and y equals k plus r sine t. So this is the general form of a circle with the center h, k, and radius r. You can check to see if this is an equation of the circle with that center, since x minus h would be r cosine theta, cosine t, and the y minus k would be r sine t. Then if you square both sides and add them, what you have is x minus h squared plus y minus k squared. This would be r squared. You can factor out an r squared. Cosine squared of t plus sine squared of t. This is simply 1, so you can ignore it. So what we get is basically r squared equals x minus h squared plus y minus k squared. And this is exactly the equation of a circle with center h and k and radius r. Okay, so try to simplify the question always for yourself. If the center is somewhere else and it's not in the origin, try to first figure out what is the answer to the origin, then shift that circle with the amount that they want. Another example would be sketch this curve. an easy way would be to relate x and y, because here it would be simply you can relate x and y. What is x squared? It would be sine squared of t. But sine squared of t is already given y. So I can say, what is y? Y equals to x squared. And we should be able to graph this. This is a parabola. Y equal to x squared. But if you don't do that, you can still draw the table. T, x, y. And you pick different t values, -2, -1, 0, 1, 2. Find out what is the corresponding value of sine. So here is the issue. If you replace -2 in there, it's going to be too much, right? So it's not going to give you something like sine of -2 is not going to be it's not going to be something like 5. So the x values are kind of bounded. This x value cannot be greater than 1. It should be always less than 1. So when you graph this y equal to x squared, you're not allowed to pass x value of 1. You have to stop at the x value of 1. Otherwise, if you draw this curve and say it will go on forever, that's not true. X is bounded here. If you replace whatever you replace for t, sine is always less than or equal to 1. Okay, so I should cut off this and at 1 and say this is it, the most I can go. On the other side, I will stop at -1 as well. So these numbers are not good choices because just you have dealing with sine. So maybe pick something like pi over, let me do, actually you're allowed to pick more angles, but I want to see, oh, yeah, so here, let's say you pick, let me start with a positive angle, 0, pi over 2. What else we have? We have pi, 3 pi half, 2 pi, and so on. You can continue. You can pick more angles like pi over 4, pi over 6 to see what happens. But if you let t to be 0, what do you get? The sine is 0. Sine squared would be similarly 0. If you pick pi half, x value would be sine of pi half, which is 1. Y value would be 1 squared. If you pick pi, you'll get 0, and y would be 0. If you pick -1, you will get -1 squared, which is 1. Similarly, you would get 0, 0. If you pick something like pi over 4, you would have root 2 over 2, and y value would be 1/2. So these points basically are 0, 1 here, and you would have root 2 over 2, and here would be 1/2. Okay, so this curve that I mentioned here is just important part of it is to notice that just because you can get rid of the sine doesn't mean that this curve is being represented exactly by that. Here are some restrictions that are hidden. The hidden restriction is the domain for x must be between 1 and -1, because sine is between 1 and -1. Therefore, the y value would be bounded as well from 1 to 0. If you square it, it should be always between 0 and 1. If you find the restriction for x, the restriction for y follows as well in this case. Okay, so make sure, draw the table, make sure that it will match up. By the way, if you continue and pick something like 3 pi, you're going to be in a loop, so you will go back to whatever pi was. You'll get 0 and 0 again. If you pick like 10 pi, it still be the same. You'll get 0, 0, and so on. Okay. Practice and practice so you can see more of these restrictions. Okay. One last thing that I want to mention is the cycloids. They're kind of nice in terms of equation, and you may see a lot of them. It doesn't really require that much It doesn't require graphing calculators and stuff. That's why I try to mention it, is to see these. If you see it on the homework, you will be familiar with it. So cycloids are basically, if you assume that you start from the origin, so this is the x and y axis, x and y axis. So this is our origin, and let a circle with the radius r start moving along this, start rotating on the, so we have a circle here, and this circle is moving forward. And by the way, as you plot these curves, always they ask you to start with the direction. So this curves will go move that way and then come back, and then goes along this curve and come back. And in the very first examples, I should have kind of mentioned those. So here, remember when we graphed this, first point was 0, 0, then we went to that point, then we went to the next one. So basically, if you increase the t, what happens is you're going to move along this curve in this direction. Okay, and the first example as well, this was our first point, and the next one, as we increase t, what happens is you're moving along this curve in that direction. Sometimes they put arrow on top of the curve just to show that what happens if you increase the t. Okay, let's go back to the cycloid. So here, if you start moving along this, if you're rotating this circle and moves along the curve, what the path that follows this circle, so this is the original point, and the path that follows this curve would be this. The path that follows the circle is this curve. So if you pick a fixed point and let that point rotate and rotate along the curve, I didn't draw it well, but it should be following this curve. So this point will come down and then it go back up along the curve, and to reach the highest value somewhere here, you'd have this big circle. So this point will reach the highest point, and it'll, as you rotate, it will continue to go down. And what you notice is a periodic behavior of this cycloids. And what is the expression representing the x coordinate is basically r theta minus sine theta. It's not difficult to see it. It would be, if you look at, let's say, the curve, I'm drawing it maybe a bit too much. So here, let's say we have a circle, and you're looking at this point somewhere here. This is the center. So basically what you notice is, that this length of the curve would be correspond to exactly that length, how much movement you have made. So this is the same as the r theta, the length of the curve corresponding to the angle theta. And this angle theta, I should draw this angle theta. And on the other side, what you have here is, this is the same as r cosine theta. So if you subtract r cosine theta, r theta minus r cosine theta, you will get the corresponding x coordinate. So the corresponding x coordinate would be r theta minus, r sine theta, not r cosine theta. Sine theta would be, maybe I chose the theta on the wrong spot. My drawing is not that good, so this is not parallel circle. So what you see is that this length would be r sine theta, and the corresponding x coordinate, maybe in the center of the circle, maybe somewhere here. There we go. There we go. Here's theta. R sine theta would be the corresponding length here. So then r sine theta would be this this side of this triangle. And if you subtract that from r theta, what you get is basically the corresponding x coordinate. You can do the same thing for the y coordinate. The height is, here is the height is exactly r, then the other side would be r cosine theta, so you subtract r minus r cosine theta, which you can factor out in r, write it as r1 minus cosine theta. So this is assuming that the circle starts from the origin and starts moving, rotating that way. Okay, so this equation is, again, with the assumption that starting from the origin. If you start from somewhere else, you'll add constant. If you had starting from x equal to k and y equal to h, then you would do this h plus that, k plus this. Just to see it, the sketch, let's try to compare. You say sketch this curve, and you notice that the structure is similar to what we have here. And this x could be written as 2 times theta minus sine theta. And y, from here, if you compare these two, you'd have noticed that the radius is r, and y would be 1 plus 2 times 1 minus cosine theta. So instead of 3, I wrote to 1 plus 2, just because I wanted to factor the 2 and write it as r times 1 minus cosine theta, and then you have this extra 1. This extra 1 is just means shift the curve up 1 unit, and that's the same as the h, as I mentioned. So this is just the cycloid. So if they ask you to sketch this, you can actually go through this angles and pick angles and replace it in there. But the fastest way would be to compare it and say, okay, now I have a cycloid that starts from, instead of starting from 0, 0, it starts from 0 and 1, because there was 0 plus this and 1 plus that. So I start from 0, 1, and I draw a cycloid of radius 2. So that means this height must be 3 at most. And the length here, what would be the length? If you go from 0, you would get 0. You can replace 0 for x. X would be 0. If you replace theta with 0, you'd get x equal to 0. And if you replace theta with 2 pi at the final time, what you get is 2 times 2 pi would be 4 pi minus sine of 2 sine of 2 pi is still 0. So you'll get 4 pi. So this last point here is 4 pi. It's basically the circumference of a circle. You will go through the whole circle by rotation. So this 4 pi is the circumference of the circle, which is the corresponding x coordinate, and the radius tells you how much height you would have, and this is halfway exactly at 2 pi. So if you replace theta with pi, what you get is the maximum y value. Okay, try to do more examples of this, but this is just an introduction to the parametric curve. I'm going to stop at this point. We'll continue as we go on.